Okay, so thank you so much for having me. And like Javier just said, my name is Maria Eckstein, and I'll be talking to you about one thing today that I think can make reinforcement learning much more powerful, and especially when we're interested in more complex kind of problem-solving type behavior, and that is abstraction or hierarchy. And I did most of the work I'll be showing today during my PhD with Ann Collins at Berkeley, but I'm not a research scientist at DeepMind. So to kick things off, I want to give one example of how our brains use hierarchy. When you see the same stimulus over and over again, say this purple oval here, you get used to it over time and your brain shows a habituation response. So it responds a little less every time the same stimulus comes up. When you see a new stimulus like this green oval, you show surprise, for example, a P300 in EEG or a peak in MEG. Now, interestingly, the same thing happens when we replace elemental stimuli with entire stimulus sequences. So when my frequent stimulus is this entire sequence of stimuli, and my oddball stimulus is this entire sequence of stimuli, then you show similar oddball response for the oddball sequence. And I think what this shows is that our brain can learn that several stimuli together should be treated just like a single stimulus. And people have called this chunking, and it's one of the simplest forms of hierarchy. Instead of operating at the level of elemental stimuli, we can now operate at the level of stimulus compounds. And to show why this is relevant, think of this example. Instead of representing an object in terms of all its individual parts, we can represent it as a single object. And that does not just save us working memory, it also makes it easy to draw inferences. For example, you can infer which parts are missing in space or in time. Abstraction is also crucial for action. When we learn a new skill, like making coffee, it first is a sequence of elemental actions, but over time it becomes automatic, and it turns into a single unified action with the same benefits for working memory and inference. And I think one thing that's extremely exciting is recursion. So you can group elements into compounds, and you can group compounds into mega compounds and mega compounds, and you can just keep going. And there's no natural limit to how far we can go. And I think that actually, so that we actually use recursion every day, I think, becomes quite clear when we think about complex concepts. For example, what are the cognitive elements of a normal distribution? And how many of those elements are actually compounds or mega compounds by themselves? So how deep is the hierarchy of abstraction? So let me tell you the main ideas for this talk. I think we have lots of evidence that humans use abstract representations and that they're extremely useful, especially for complex problems. And I'll show a few examples of this later. And I think everything we already know about human abstraction could also be useful in other domains. For example, like many of my prior speakers have already alluded to in AI, some of the most burning problems could be resolved if we just had the right abstract representation. For example, most AI algorithms fail when we teach them on 10 very similar tasks and then test them on an 11th task, which is just as similar. But if this algorithm had human-like abstraction, it would be trivial to transfer the knowledge in the right way. However, I think there's a big problem if you want to apply everything we know about human cognition to a different domain like AI. And that is that different fields speak different languages. So I think a big step really is to make our own research more generalizable. And that likely means using some kind of shared language like formal computational model. Okay, so with that, let me show you one study we did where we tried to look into human abstract representations. So what we wanted to understand here were really two things. One of them is, can brains create much more complex compounds than just the chunks I showed you before? For example, could those compounds be defined by the rules of logic? And the second question was if participants can really create mega compounds on top of compounds. So can we create this kind of multi-level hierarchy? Before I start, let me tell you two cool facts about pupillometry, because we use pupillometry in this study. One is that your pupils dilate when you're surprised. This dilation is often called violation of expectation, or VOE. So in a typical oddball task, the oddball element will create a big bump in pupil dilation. And the second is that your pupils dilate when you're adding things to your working memory. So if somebody tells you their phone number and you're trying to memorize it, your pupils will get a little bit bigger with each number you hear. So what was the task? We used an oddball design. So participants see one stimulus after another, and we measure pupillary VOEs to see if they recognize the oddball. But this time, the oddball is not a rare stimulus. Instead, we teach participants an arbitrary rule for what an oddball is. And because we were interested in complex compounds, we used a complex rule. If you know the card game set, this will sound very familiar. So the rule has a logical AND at the top level, then a logical OR, and then patterns Match here means that the feature is the same on all stimuli. For example, all stimuli are red. Span means that the feature is different on each stimuli. For example, one is red, one is green, and one is blue. So this rule is multidimensional. You have to integrate across all features, color, shape, and fill to make it work. The rule is also flexible. So sub-rules can combine differently each time, and every trial will look different. So let me just show you a few examples. Here, all the stimuli have the same color, the same feel, and the same shape. That means they match on each feature, and the rule is valid. There's no oddball. Here, all the stimuli have the same color and feel, so they match, but they have different shapes, so they span. And again, the rule is valid. There is no oddball. Here's an example, an invalid example. The stimuli all have the same shape, so they match, but they don't have a valid pattern for color or fill, and that creates an oddball, the blue stimulus here. Here's an invalid version of the second example. Here we replace the fourth item with an oddball, and here are the remaining trial types. The rule is valid when you have any combination of match or span, and when we replace any stimulus in a valid trial with an oddball, we create an invalid trial. So what did we find? How did they recognize the oddballs? Here I'm showing you pupil dilation on the y-axis and time within a trial on the x-axis. And you see that each stimulus, as 1 is 2 and so on, creates a bump in pupil dilation because new information is added to working memory. The gray line shows trials where the rule is valid. 4 equal bumps, no evidence for a VOE. The red line shows where the fourth stimulus is an oddball. And you see a huge VOE at the fourth item. In other words, participants did recognize the rule validation. What this means is the participants really internalized our complex arbitrary rule to a point where rule violation creates a physiological oddball response. The VOE also means the participants formed expectation about the rule. Without expectation, there would not be a violation of expectation. So they did not just passively recognize the rule, they actively generated prediction. I think this really shows that our cognitive mechanism for abstraction is extremely powerful. We don't just create chunks when something is repeated verbatim. We understand much more complex patterns, and we internalize them quickly and are able to use them to generate predictions. So our second question was if participants understood the multi-level hierarchy in this task, right? And if that was helpful. I'm showing the 4 trial types here again at the bottom. M stands for match, S stands for span, and we have the valid combinations MMM, MMS, MSS, and SSS. What you see is that MMM and SSS repeat the same pattern 3 times. But MMS and MSS are mixed. So to know if participants understood the hierarchy, we checked if they pick up on this exact regularity. And to see if they pick up on it, we look at pupil dilation. If you remember, pupil dilation tracks working memory load, right? So if participants pick up on the hierarchy, they can save working memory load on MMM and SSS because of this repetition. And the likelihood should be smaller than if they did not pick up on it. So this is the expected pupil dilation for each trial type if we just enumerate all features not using hierarchy. But if we use hierarchy, we can save load on MMM and SSS trial, and pupil dilation should be lower. So what we found was that some participants looked non-hierarchical and some looked hierarchical. So not everyone seemed to use the abstract regularity. Hierarchical participants responded faster on those MMM and SSS trials. So it seems like the hierarchy really helped when there was a regularity. But non-hierarchical participants were more accurate on mixed trials. So it also seems like the hierarchy actually hurt when there was no regularity. And I think this is an interesting point because every time we create an abstraction, we need to decide which information we want to abstract away and lose. So hierarchical representation can be helpful in some situations, like the MMM and SSS trials here, and at the same time hurt in other situations, like in those mixed trials. So I think what this study shows is that as humans, we quickly internalize complex, flexible hierarchical rules, and we recognize rule violations on the fly. We don't just receive inputs passively, but we actively build a structured representation and use it to create expectations about the future. I think this kind of mental model building is fascinating, and we still don't know how to build machines to do anything close to humans, so there's a lot we can still learn. And I think secondly, recognizing hierarchy can save you cognitive resources and can make you more efficient at problem solving if it has the right structure. So the million-dollar question really is how to know which abstraction will be right for a problem. It turns out humans are very good at this, but it's still an open question in AI. And my third study will try to understand a little better how humans create those abstractions. But before we get there, I want to come back to another issue, and that of using a shared language of creating computational models. So in the next study, we try to create such a model and show that it captures a lot of human behaviors related to hierarchy and reinforcement learning. So what do I mean by hierarchical reinforcement learning, or HRL? HRL just means that you use the same RL algorithm at different levels of abstraction. So for example, you could use RL to associate a visual stimulus in the button press, or to associate an abstract context within an entire behavioral strategy or a task. You use RL, but the RL algorithm operates on different entities, either very concrete one or very abstract ones. So let me give you one example. You're at home and you need to decide what to have for breakfast. For drinks, you could choose coffee or orange juice. And for food, you could choose granola or pastries. At your local grocery store, the coffee and granola are good, but orange juice and pastries are not. So over time, you learn to go with coffee and granola. In terms of RL, you're getting positive reward prediction errors every time you choose coffee and granola, negative reward prediction errors every time you choose orange juice or pastry. So over time, coffee and granola will have higher values and you will consistently choose them. And indeed, when we give this task to participants in the lab with slightly different stimuli, they all seem to be using RL to learn which responses are correct for each stimulus. Now let's imagine you go on a holiday and the coffee and granola are terrible, but orange juice and pastries are amazing. How would RL deal with this situation? This is surprisingly tricky because we don't want to override our old values because we'll need them again when we're back home. But if we don't override them, we'll keep making bad choices during the holiday. So let's see what our participants seem to do to solve that problem. They created task sets. A task set is a set of stimulus action values that applies in some context. Say, it tells you what to have for breakfast at home. And participants solve the problem by just creating multiple task sets, one for at home and one for the holiday. Now the whole problem is solved as long as they choose the right task set for each context. So how did they choose task sets? We used modeling to answer that question and found that they again use reinforcement learning. So they learned a value for each task set in each context to choose it. So if we look at both sides of this slide, we see that our participants used HRL because they used RL at two different levels of abstraction. At the low level, on the left, they associated stimuli and actions using RL. And at the high level on the right, they associated context and task sets using RL. So why is it a good idea to use HRL? One reason is that HRL can help with inference. Let me show you what I mean. In our task, participants can usually see the context, but at some point we removed it. So at this point, participants had to infer it to make the correct choices. And we found that participants were quite good at this. For example, when a participant randomly guessed orange juice in a drink trial and got a reward, they seemed to infer that they were in the holiday context because they immediately started picking pastries as well, which is the correct very simple. Orange juice is the correct task set. So the reward told participants directly which task set to choose. And the task set already contains all the right stimulus action values for the context. If it contains orange juice, it automatically also contains pastries. So what looks like inference here could just be simple picking of the rewarded task set. And I also mentioned that hierarchy is great for generalization. So if you don't generalize, you have to start learning from scratch in every new context. Whereas generalization helps us do something reasonable right from the start. So when we put participants into completely new context, XYZ here in this task, the choices had a lot of structure right from the start. This workflow shows participants' initial response profile, and you can see that they have a very clear preference for some actions over others, even though they've never seen this context before. How did they come up with this particular strategy? Part of it were task sets and values. Participants reactivate previous task sets when they see a new context, and they especially reactivate tasks that have had high values in the past. So to sum up this study, I showed you that our participants seemed to use HRL when they had to learn about different contexts. They learned RL values at the lower level of abstraction for stimuli and actions, and at the high level for context and task sets. And when the context was hidden, they can use task sets to do inference, and in a new context, they can use task sets to generalize. This table summarizes all HRL makes in this task, one per row. And the green check marks show which ones are met by different models. RL here stands for classic non-hierarchical RL, and HBase stands for hierarchical Bayesian model. And you see that both captures some phenomena, but only RL captures all of them, and humans show all markers of HRL as well. So I think what this study shows is that RL has a bigger potential than we often think. RL does not just apply to stimulus response learning. It can also explain many interesting phenomena in the cognitive domain if we add abstraction. And maybe our two-level hierarchy is just the tip of the iceberg. Maybe humans use meta task sets and meta context to know how to learn task sets depending on the context. Or maybe you learn meta task sets in meta context. And each level uses the same rule for learning and allows for generalization, inference, and so on, but each applies to a more abstract and broad set of experiences. So what can we do with this model? Having a precise algorithm means we can apply to different data, we can make predictions, we can formally compare to other algorithms, we can expand on it, and of course, we can apply it to other fields like AI. Now let me turn to my last question. How do we create hierarchical representation? So this is the million-dollar question I mentioned before. To answer that question, we designed a task where we could observe how participants were building a new hierarchy from scratch. So participants had to learn sequences of 4 actions to get a reward, but we helped them break them down into 2 action sequences. So we made the task hierarchical by creating chunks. What I'm showing here at the bottom is the raw search space based on individual actions. But the top shows the chunked or the hierarchical counterpart, where the search space is much smaller. So for example, if the correct sequence is BACB, you need search 4 levels steep in your representation if it is non-hierarchical. But you only need to go 2 levels steep when your representation is hierarchical. So what we learned in the study were really 2 things. One of them is that participants were really quick at picking up those 2 action sequences. We gave them really minimal feedback and no rewards at all, but they used the sequences basically right away. I'm showing trials here on the x-axis and frequency on the y-axis, and you see that the red line, the non-sequences, plummet really fast, and the blue line, the 2 action sequences, just takes off. And the second thing we learned was that different levels of abstraction seem to play different roles. After participants did the task for a while, we changed the rules of the game to see how participants adapt. In one condition, we kept the same 2 action sequences, but we changed the rest. We call this the low-level transfer because the low level of the hierarchy can be transferred now. But in the other condition, we changed a few actions within the 2 action sequences and kept the rest the same. And this is the high-level transfer. So what we found was that participants recover much faster when they could transfer the low level. I think what this shows is that the low level had become automated and was therefore difficult to unlearn, but the high level stayed flexible and malleable. And this reminds me of a lot of cognitive phenomena. For example, language, where it is really hard to relearn the most basic level, to learn new phonemes. But the top is extremely flexible, which allows us to create ever new and creative sentences. So I hope I convinced you all that abstraction is very exciting and also that humans are quite good at it and use it all the time. Abstraction makes it possible to solve problems that would otherwise face the course of dimensionality, which is an explosion of possibility that makes it completely impossible. For example, if you use action chunks instead of individual actions, you drastically reduce the number of steps you have to plan ahead. You also save working memory capacity if you recognize higher order regularities, because it allows you to compress your representation more efficiently. Abstraction also helps us make intelligent predictions. If we internalize complex abstract patterns in our world, we can run them forward and recognize when patterns are violated. And a pattern violation is usually very useful information because it means that something fundamentally has changed in your world and you should really pay attention. Abstraction is also extremely useful for generalization because we can port entire strategy to new context now. And something that looks like costly Bayesian inference could also be the simple reactivation of an abstract strategy. For example, if part of a chair is hidden, you can infer the rest because you know what a chair looks like. And when an event is unfolding over time, you can predict what happens next if you have an abstract understanding of that event. I think that a lot of intelligent behavior is really grounded in abstraction in some of those ways. And I think because abstraction is so powerful, we should integrate it into our L models. Abstraction could turn a model that explains lever pressing for a reward into one that explains complex decision-making and hypothesis testing in a multidimensional world. So I showed you that this is possible to make a computational model of hierarchical RL. And then it actually explains human behavior quite well along many dimensions. So I wanted to close with one project that I think highlights some beneficial crossing between the disciplines. And that was my intern project at DeepMind. So we had an AI agent that was playing a game where events were unfolding at different timescales. So the agent had to select strategies at the high level and then execute them step by step at the low level. The agent was a neural network and the representation was hierarchical. What I'm showing here in the center are the neural activations in the abstract representation over time. And the plots around it are just screenshots of the task that show the low-level policy. And all I want to highlight here is really that the agent learned very smart, orthogonal, high-level strategies, much like humans. And indeed, it generalized much better than other flat architectures. Okay, so with that, I want to thank my PhD advisor, Anne, in the CCN lab, Sylvia in the Bungie lab, and Sasha and the people at DeepMind who helped me with this project. Thank you.